Let's open the floor for questions. We have 10 to 15 minutes, so let's have a question and answer session. Yes, it's over there, gentlemen.
Related to the first talk, I would like to commend the authors to push this CFD initiative through. But the question still remains that we're using 2D simulations, and probably you're using RANs, and if you use large eddy simulation 3D and with inflow conditions, it's quite a challenge, which you also realize. With the collaboration with a very large computational facility, how far do you see this thing coming to a realization?
So I guess the real question is like, how much computational resources do we have available to us? So I just had a short discussion with the CFD guys last night, because they're the domain experts. I just give them the model and tell them to run it. But they're part of a research group, and they're running about 128 cores, and they're saying like Ford or GM are running cores in the range of 1,000 cores. So the scale of the computational facilities available to us in the room typically is quite trivial compared to what's available in industry. So the question is, can we maybe run these simulations on Amazon Web Services or something like that, and rent those computational resources as opposed to running it in-house? So that's something we chatted about, but I don't think we're quite there yet. So for the 2D stuff, we did it in Singapore. I did it in Singapore, so that's just a regular desktop. For the 3D stuff, they ran it on their cluster. But if we really actually want to go to 3D transient simulations, then we'll probably have to rent computational resources externally. It's just not feasible to own those resources, and because for once a month kind of situations. So I hope that kind of addresses that question. Thanks.
Andy, Ben Coxon from Oricon. My question relates to your study on energy consumption and use, which is to be commended, obviously. Just in terms of the energy consumption from a materials point of view, and getting the materials there, and actually the production of the materials themselves, have you got any high-level comments? You obviously saw some opportunity in the in-use piece. Have you got any comment about the high-level opportunities in terms of, from a materials point of view, the capital cost, so to speak?
Thanks for your questions. If I can just say the question is to do with the amount of material used in, which one, the Energy Tower project?
That's right. No, your Energy
Right.
Tower project
Right.
is an in-use solution, effectively.
Right.
You obviously looked at that rather than you saw some significant opportunities there, versus the opportunities of just tall buildings, material consumption, etc. What high-level opportunities do you see in that domain?
Okay. That's a very interesting question, actually. Tall buildings actually waste an enormous amount of material during their construction process. We've all been on construction, building sites, and kind of worked our way through the rubble that's there and the offcuts and all that sort of stuff. If you actually add up how much material physically goes into a tall building versus what's actually on the drawing, you'll find there's a significant gap. So one of the easiest places to look for savings, if you will, is to start contemplating prefabrication, pre-engineering things, because the amount of wastage, particularly on site, can be reduced absolutely significantly. The project we're currently doing, the J220 project, it's a structural steel solution we've chosen there, and that's all prefabricated, pre-engineered, if you will. So actually, by the time it gets to site, there's virtually, I won't say there's zero wastage, but there's almost zero expendables on site and wastage and so on. So material usage is very carefully controlled. So I guess that kind of partly answers your question.
No, that does, and that reflects our own experience that steel, despite being high on the embodied energy stakes, is actually really good for the wastage reasons. But
Yeah.
thank you. That's good. Thank you.
Hello, I'm Hashima from, I'm developer of KLCC Petronas Twin Towers. Question to Mr. Zhao. You mentioned that rounding off the columns, edge columns, would reduce wind loads by about 20%. Would this be significant in countries like Malaysia, where the wind load is not so high? Thank you.
That's really depend on the wind. The wind speed and wind pressure on the buildings. And even the wind is not that high, but for super tower, when it gets higher, the wind gets stronger. And we talk about the super tall building as like a vertical cantilever. Even it's a smaller wind on top, since it gets tall, you get very large overturning moment. So it's always beneficial if you can minimize the wind load on top of the building. Did I answer your question?
Can I add something? Do you mind? Do you mind if I can add something to perhaps clarify? One of the key design parameters for super tall buildings is the crosswind acceleration due to vortex shedding. That actually happens at very low wind speeds. Okay, so I think maybe your question was phrased with the maximum wind speeds in mind, but actually some of the highest loadings on a tall building are quite modest winds. So the idea is that a wind that occurs quite frequently, a wind that occurs once every 10 years, in fact, which is not the full strength design wind, but just quite a modest wind. That wind is the one that's actually really going to get the building rolling because of the way that the vortex shedding works, okay? So to answer your question then, rounding corners and kind of eliminating vortex shedding works no matter where you are in the world. It's just a great thing to do. And whether we're designing for typhoons like we are in this part of the world, or if we're not designing for typhoons like you don't in Malaysia, it doesn't make any difference. If you can get rid of the vortex shedding, you're on a winner.
Can we bring the mobile phone?
Anil here at Bureau Happold. Andy, I've got a couple of questions for you. Great to hear about lessons learned. I think that we as structural engineers of tall buildings tend to hide some of the lessons. We think we get it all right. Andy, it's interesting in terms of the monitoring of the towers, the stiffness and damping, but you didn't come up with any conclusions, and I'm interested in your conclusions on that in terms of damping levels and stiffness levels compared with theoretical predictions.
Thanks, Anil. Look, it's the chestnut question, isn't it? It's the thorny question that we've all got as tall building engineers. What is the damping level? Okay, so the way to answer it is quite simple. First of all, we look at are there any theoretical models around that predict? Can we simulate what the damping levels are? And the answer is no. We actually there are no numerical models that actually figure out what the damping level is. So that's a good question. The next is, are there any test results? Have we actually measured many tall buildings? And the answer is sadly no, actually. I mean, I've got a pretty good library of all the buildings that have ever been measured, significant buildings, and that's a pretty small library, sadly. I'd have to say probably most buildings above 400 or 500 metres have been measured for damping, but there aren't many of those. There's maybe 10. So do we really know? We don't really know, to be honest. Have any of these buildings really been pushed to their limit? Like, has a tall building ever really experienced the full force of a typhoon? No, actually, not really. There's some pretty good measurements from when Cyclone Alasia went through the southern part of the US about 20 or 30 years ago. I think there's a 70-story building there that got up to about, they think it got to something like the 50-year return period wind load, something like that. Other than that, there isn't much, actually. So we don't know a whole lot, to be honest. What we did with Burj, we kind of used it as a test bed to try and answer some of these questions. And what I can tell you is a sort of headline summary. What I can tell you is we measured damping in the building at various stages of construction. So The cladding contract was very late on that project for whatever reason, and the silver lining in that dark cloud was that it gave us a chance to measure the damping on a raw concrete frame that's 600 metres tall, and we got a number there. And then when the cladding arrived, the damping significantly increased, and I mean significantly increased. And when the MEP services and stuff started getting inside the building, it increased again. So those things certainly do increase the damping levels, but even so, we're still talking, call it 1%. Call it 1% damping. And I know a lot of North American practice, you know, for 10-year return period winds, you'll be using 2% damping. To be honest, I'm going to throw it right out there, guys. There is absolutely no evidence that suggests that 2% damping exists for those sort of movements. You know, a 1-year return period wind, it's not, there's no measurement that says that, okay? I think it's conventional practice, but I'm really struggling to find any measurements that actually tell me that's the case. I don't know, Neil, does that help a little? The other thing I might add, the larger the building, the taller the building, the closer the measurements come to the computer models. And you know, I think the reason for that is that these very tall buildings are designed for quite large loads, and they're never going to see those loads. On a normal day, when we're shaking it around with a crane, or you know, there's a late afternoon sea breeze coming through, and we're getting some nice measurements off Burj, and we can kind of figure the damping again. The building's not moving around much. The average stress in the column is really low, and so it is elastic. It's truly elastic, and that mirrors, you know, the way we analyse these things. If you, in a concrete building, if you measure the real value of the modulus, I mean, not out of a code, just go measure the real value at 90 days, stick that in your computer model. On Burj and those sort of buildings, we get second decimal place agreement. Second decimal place agreement on periods and frequencies between computer models and the real thing. I'm not sure if that observation would apply to smaller buildings, but it's certainly, so I guess one takeaway conclusion is the bigger the building, the closer you're probably going to get. But the bigger conclusion of all of that is that the damping levels in these buildings are very low. It is very low. You need to deal with that. You cannot assume that you're getting 2-3% damping. There's just no evidence for it.
Let's take last question.
Thank you, Andy, for this the monitoring information. We are NPS auditors from Russia, and we actually specialize in structural monitoring. In Russia, there's a regulation that you actually have to have a monitoring system if a building is higher than 100 meters. So we have 200 buildings under monitoring. About the damping issue, I think we have enough measurements to actually do these kind of calculations. We just need time and people to do this kind of management. But do you feel any need for other structural monitoring systems in other countries? Do you think there's a need for people, for buildings to have these systems for management or for these kind of damping calculations?
Thank you for the question is, should we be measuring the things we create? Absolutely we should be. And we take it to our owners and developers that I put it to my owners and developers that I actually think it's their responsibility to measure the things that we build. Settlements of foundations, column shortening, lateral movements under wind load, all this kind of stuff. And they say to me, why? Why do I want to invest in a system such as yours? Okay, it's a good question. We try and cook up answers to that. We try and invent answers to do with fatigue on steel structures and all sorts of stuff. Because actually the right answer, the real answer is that, in my view, it's their responsibility to take the level of knowledge that we have right now and increase it. In order to design and build their building, they've taken a big scoop out of the pool of knowledge, and they've used all that stuff, okay? In my view, they need to put something back. So that's a personal view. You can't run that argument against the developer because it doesn't work. I know it doesn't work from personal experience, but you can wrap it around with other stuff. You can try and put the kind of lift control argument against it, but that kind of doesn't work either because Otis and the guys have they got their own lift control stuff, so that doesn't really work. You can wrap a fatigue argument around it, and that works with a steel building. maintenance and serviceability. The argument you can't wrap around it, sadly, is the right argument, which is it actually is their responsibility to put something back.
Right. I think it's time for lunch. The Congress people just remind me the time control now. Thank you very much for attending this morning's session. We got a very interesting, very inspiring presentations. Let's give a round of applause for the three presenters. Thank you.